Hi, we're Group 6 and we're presenting our project on predicting the energy demand in Quebec. All of the sectors shown in this graph rely on a consistent supply of power. The legacy system of urban energy includes its generation, transmission, and distribution. Hydro Quebec has been responsible for these three branches of infrastructure since 1944. In our project, we're using weather and energy data and supervised learning to apply SVR, Random Forest, and LSTM in a predictive model. As an energy provider, Hydro Quebec faces the challenge of having to provide a larger or smaller supply of energy depending on the stochastic behavior of its residents. It should have a resilient energy grid against record-breaking cold temperatures and the unprecedented weather conditions due to global climate change. We're proposing a model that predicts the hourly electricity demand based on weather conditions throughout the province.
We are trying to see the effects of weather on the energy demand of Quebec, so we first need to obtain weather attribute data and use a method to see which of those attributes are most strongly correlated with energy demand. Secondly, we need to identify weather stations around the province that best represent the condition of the entirety of Quebec. Then we can feed our machine learning models with relevant data to A, predict the hourly energy demand of the province for a given day, and B, predict the peak hourly energy demand of the province for a given day. From our literature reviews, we noted that temperature, humidity, and wind speed are attributes that are useful in predicting energy demand. So we will use the Spearman correlation matrix to see which of those attributes have the highest correlations that will be useful in our machine learning models. The attributes of weak correlations will be discarded.
From literature review, we have seen a strong relationship between urbanization and energy demand. Therefore, from over 273 stations with hourly data, we decided to use for our models the 5 most populated cities in Quebec. These 5 cities account for 80% of the population, and we decided to use the weather stations of the airports of these cities since they have less missing data and due to their governmental relevance in the safety of people.
Objective 3 is to predict the hourly energy demand of the province. Since we have labeled continuous weather data from Objectives 1 and 2, we will use machine learning regression models to predict the hourly demand. The dark blue curve in this figure is temperature in Montreal. We'll split the energy data into 2 years for training the model, seen in light blue, and 1 year for testing the model, seen in red. So we'll feed our energy data and our weather data into models for regression. We've chosen to compare the algorithms Random Forest Regression and Support Vector Regression as they are relevant for load forecasting and based on ideas from class. We've also chosen to explore long short-term memory, or LSTM, because of how it takes advantage of time series data. Forecasting hourly demand will allow us to identify peaks. This figure shows the energy demand on a Monday in the winter, spring, summer, and fall of 2019, and it seems that on Monday, January 7th of 2019, the peaks occur around 7 a.m. and 5 p.m. If we look at this entire week in January, we can see that those are just local maxima, and the true maximum for the week was Friday night. We will explore these 3 models to predict the daily and weekly peaks in energy demand.
We're considering 3 years of data on an hourly basis, and we have around 26,000 examples in our dataset. The main attributes of energy consumption are the date, time, and electricity volume that the generator supplies and sends to the distributor. Here, the monthly box plot of the electrical load is presented, and we can observe some outliers for different months. Also, considering this graph, we can find the high demand periods. Inspired by previous studies, we're working with these attributes among all of the available attributes in the weather data. Looking at these graphs, temperature and load consumption are inversely related. Also, regarding other attributes, we might figure out to what extent wind speed peaks affect the load consumption.
To deal with missing data like temperature, we decided to use KNN with different K values. We've started the iterative process between choosing weather stations based on population and selected weather variables. Our early finding confirms the temperature of the selected weather stations are strongly correlated with energy demand of the province. This agrees with our method in Objective 1 to choose weather stations corresponding to high population centers. The other variables, however, did not appear strongly correlated in this analysis, but we have yet to account for the seasonality that may reveal the correlation between energy and humidity in the summer or wind chill in winter. Our remaining steps include applying different machine learning regression models, evaluating the performance of forecasting with different models for different seasons, and selecting the most accurate model.